Hey everyone, welcome back to ML Works. In this video, we'll learn how to fine-tune an LLM on Apple Silicon using MLX. So MLX is the Apple's official machine learning framework which offers a tailored approach to run LoRA or QLoRA fine-tuning directly on the Apple Silicon chip. Now, there are other changes with respect to the architecture when it comes to Apple Silicon. One of them is the unified memory architecture, where you allow CPU, GPU, and neural engine to access a single pool of high bandwidth RAM. So, this is very different from what we see with NVIDIA GPU, which has a separate VRAM for itself. So when it comes to the task, we'll be fine tuning a 1 billion parameter model compressed to a 4-bit precision, and thus making us to only use less than 4 GB of RAM to train a LLM using QLoRA. First step is to install the package, which is mlx-lm. So let me run this. So if you are doing it for the first time, I would recommend creating a virtual environment and then installing this package, and then you can go ahead and verify if the GPU is available or not. For this, you just have to import mlx.core as mx, print GPU available, mx.default devices. For this, you don't have to do all this. Let me just take this out and print this here. So we have this output here, which is device has GPU. Now coming to the data set, so the MLX expects your training, validation and testing data set to be organized inside a single folder in a format called as JSON lines. So here first we'll be importing JSON and then load dataset module, and we'll be downloading alpaca-cleaned dataset and we'll be splitting it using the train keyword, and we'll get our dataset, and then we'll split the dataset with test size as 0.05% and seed as 42. So let me run this as well. So once you have downloaded the dataset and split the dataset, you have to convert the alpaca cleaned data to MLX format. So let us see what it is. So here we have our data split, and we take each item, and then each item contains the instruction, which is your user prompt. Then each item also contains the input, will be turned into your context. And then we have our mlx underscore line, which is nothing but the format that we want to follow. So we have messages. First is the role, which is system role, and the content is you are a helpful assistant. Then we have a next role, which is user, and which takes in the user prompt, and then we have assistant, which takes the item output. So this is the part of your data set again. Then we write everything into our file which we created here, and then we write out the data into the directory, which is data directory, and we convert to MLX format by calling this function, and we pass in the split dataset train and split dataset test into this specific folder and in this specific file name. Let me run this here. And then comes the fine tuning part, where we use the mlx_lm.LoRA, which freezes the core model parameter and updates the low rank matrices, which is the core part of LoRA adaptation. And this will ensure that we save memory and compute cycle, because we are not going to update all the billion parameters. We'll just be updating the low rank matrices like A and B, which is part of your LoRA architecture. So here first we take in our mlx_lm.LoRA. We say which model we need to fine tune. We want to fine tune 1 billion parameter instruction model at 4-bit, which is of 4-bit. And then we pass in the data set, and then we want to train. The number of steps is the iteration. The batch size is we want to process 2 data points simultaneously, and we have the number of layers for the LoRA that we want to fine tune. This is the last 16 layers of the model, and then we set the learning rate as 1 e power minus 5, and then we have adapter path where we'll be storing our fine tuned model or the LoRA adapter. So let me run this. Once it is executed, we'll be getting our fine tuned model or LoRA adapter, which will be stored in this specific path. So while this is training, the next step is we can either use CLI command for performing the inference, otherwise we can make use of the programmatic inference. So let's wait for this to conclude here. So iteration 1 validation loss was 2.814, validation took 15.97 seconds. This is iteration 1. Let's see when it comes to iteration 10, what is the validation loss and how long it took. So the validation loss moved from 2.8 to 1.36 after iteration 10. So you can increase this iteration to even 500 and you can continuously see what is the validation loss is. So the final weights are saved in this specific location as safe tensors. Now we can go ahead and perform the inference. So you can either do this CLI command or you can take up this programmatic inference. So we take mlx-lm, we import load and generate. So we load this specific model along with the adapter path where we have stored our adapters which we fine-tuned recently. And then we go to the messages where we set the system prompt and then we set the user prompt, create a punchy marketing tagline for a local coffee shop. Okay, and then we send this to our tokenizer which will create the chat template for this message and we'll get our prompt, and this prompt will be then sent to the generate module where we'll pass the model along with the tokenizer where we send the prompt. At max we want to get the token 200 and the verbose is set as true, shows the generation speed and details. So let me run this here. It should be quite quick. So it loaded all the files related to the models and then it generated the response. So here are few options: brewing a better day, 1 cup at a time. Okay, all these are different taglines. Which one do you like best? And this is the verbose message that we get because of this parameter that we set here. So the prompt is 54 tokens and the generation is 74 tokens, that is 80.685 tokens per second. And peak memory is 0.911 GB. Now this is how we perform the inference. Now what we have to do is we can combine the adapter with our model such that we can deploy them. So to do that we make use of something called as mlx-lm.fuse such that we can combine our adapter model with our core model. So to create a single standalone model folder that contains your base model and your fine-tuned model, we use a merge flag. So here we have this dot fuse which is used for merging these two models. One is the adapter and this is the core model, and we combine these two and store it inside this specific path. So let me run this here, and you can run this fused model using any MLX inference suite like Llama or desktop wrappers like LM Studio. So if you go here in this section, you will notice that we'll have my fine-tuned Llama which contains both your adapter as well as the core model. So this is how you have to fine-tune an LLM on Apple Silicon and how you can merge the adapter with your core model and use it for deployment. So with this, I'll be concluding this video. Thank you for watching.